Okay, welcome once again. We are in solutions. This is unit 2 of chemistry, class 12 chemistry of West Bengal Council of Higher Secondary Education. Now this is my third lecture on this particular chapter. The last lecture was telecast on 27th of April. So I would advise you to go through that lecture before you see this lecture. In order to follow it clearly. Okay, so we are studying about solutions, which is unit 2 of West Bengal Council of Higher Secondary Education, and the topic we are in currently is solubility of gas in a liquid. Now in the last lecture we have discussed how solubility of a gas depends upon pressure. Okay, so dependence upon pressure, dependence on pressure. Now we have seen that qualitatively we have seen that when we go to high altitude we have got difficulty in breathing. Why? Because at high altitude the pressure, atmospheric pressure is less, so less amount of oxygen will dissolve in our blood. Okay, so therefore we can say that solubility decreases when pressure decreases. Okay, otherwise we can say solubility of a gas in a liquid increases when the pressure increases. Okay, now on the same topic, that is dependence of solubility of a gas on pressure of the gas. Okay, we have a very important law. That law is known as the Henry's law. Okay, so Henry's law, okay, what we discussed in the last lesson was a qualitative dependence of pressure, of solubility of pressure. Now we formulate a law, or we formulate a relation by which we will find a quantitative dependence of solubility on pressure of the gas. Okay, so before we study Henry's law, I want you to understand first of all the meaning of partial pressure. Okay, so this is partial pressure of a gas in a mixture, partial pressure of a gas in a mixture. Now this is something that you might have studied in class 11. Okay, so whenever we have a mixture of gas, supposing we have a bottle, a box which contains nitrogen and oxygen. We have a box containing both nitrogen gas and oxygen gas. Supposing the total pressure of the gas, the mixture of the gas is 200 mm of mercury. Okay, supposing the total pressure of the gas in this box is 200 millimeter of mercury. Okay, now the pressure of the gas inside will be due to what? Will be due to the pressure of nitrogen. Now in this total pressure 200 millimeter, nitrogen will be contributing to this total pressure, and oxygen will also be contributing to the total pressure. Okay, so the contribution of nitrogen is known as the partial pressure of nitrogen, and the contribution of oxygen will be known as the partial pressure of oxygen. Okay, so it's almost like concentration. Okay, so partial pressure. Okay, we will not write the definition of partial pressure because you will find this in class 11 textbooks. Okay, so partial pressure of a gas in a mixture. Remember, mixture. Okay, we talk about partial pressure only when the gas is present in a mixture. Okay, if there is only nitrogen gas, then we don't talk about partial pressure. We just talk about pressure of nitrogen. Okay, so partial pressure we talk when do we bring the topic of partial pressure? Only when a gas is present as a mixture of two or more gases. Okay, so partial pressure of a gas in a mixture. Definition of partial pressure. See, partial pressure of a gas in a mixture is the pressure that the gas will exert if it occupied the same volume all by itself. Okay, that means, so in this particular box, if oxygen was absent, just imagine that oxygen was absent. If oxygen is absent, or if oxygen was removed somehow, keeping nitrogen there. Okay, then you can imagine the pressure of the gas will not be 200 mm. Okay, because when you remove the oxygen, the pressure will drop to 200 mm. Okay, supposing pressure due to nitrogen only is 120 mm. Okay, so if oxygen is removed, then the pressure exerted by nitrogen only in the same box is 120 mm of mercury. Okay, this 120 mm of mercury is known as the partial pressure of nitrogen. Okay, and this is represented by a small letter P with N2. Small letter P N2 implies partial pressure of nitrogen. All right. Now, in the same way, pressure due to oxygen or the partial pressure of oxygen. Okay, again in the same box, supposing box containing nitrogen and oxygen together exerting a pressure of 200 millimeter of mercury. Supposing you somehow remove the nitrogen part. If you remove nitrogen from the mixture, what happens? Then the total pressure will be exerted only by oxygen because nitrogen is absent. Okay, supposing the total pressure of due to oxygen is 80 millimeter of mercury. Now this 80 millimeter of mercury will be known as the partial pressure of oxygen in the mixture. Okay, right. So you can see that this total pressure P total is always equal to the partial the sum of the partial pressure Pn2 plus PO2. So that is equal to 120 plus 80 equal to 200 mm. So this is the meaning of partial pressure. This is a small important concept that everybody must have in their mind, that partial pressure is the pressure that a gas will exert if it was present alone in that volume. Okay, and for any gas, if you add the partial pressures, then you get the total pressure. Okay, so now let's come back to our main topic, which is the Henry's law. The Henry's law now. Okay, so Henry's law, I told you that Henry's law is a law which describes how solubility of a gas depends on the pressure of the gas. Okay, so it states that this is the statement: the solubility of a gas in a liquid is directly proportional to partial pressure of the gas. Okay, so two things you have to see here. First of all, partial pressure of the gas. Okay, solubility depends upon the partial pressure. And okay, the next thing you have to remember is the solubility of the gas. Okay, so first of all, let's explain this diagrammatically. Okay, supposing we have gas. This is supposing there we have two gas A and B. So this bigger one is gas A and the smaller one is gas molecule B. Okay, so whenever we have mixture of gas A and B, okay, on top of a liquid. Okay, so what happens? The molecules will dissolve. Some of the molecules will dissolve. Okay, some of the molecules will dissolve in the gas. Okay, so you can see molecules of A is also dissolving in the gas, and the molecules of B is also dissolving in the the molecules of A is also dissolving in the liquid. The molecules of gas B is also dissolving in the liquid. Okay, all right. Now, according to Henry's law, what is solubility again? Solubility is how much of gas the quantity of a gas A that dissolves in certain volume of the liquid is the solubility. Okay. Now, according to Henry's law, this solubility, how much of the gas dissolves, how much of A dissolves, how much of B dissolves, that is the solubility. That solubility is proportional to the partial pressure of the gas. Okay. The solubility is that means the more the partial pressure, the more will be the solubility. Okay. So, the more partial pressure of A, the more will be the solubility of A. The more the partial pressure of B, more will be the solubility of B. Okay. So, if we have a situation like in this case nitrogen and oxygen, okay. So, see you have a box containing nitrogen and oxygen. Supposing you can just imagine that this nitrogen and oxygen is in a box, and on the bottom of the box we have got some water. We have got nitrogen and oxygen. On the bottom of the box we have some water. Okay. So, now you can see from here the total pressure is 200, but the partial pressure of nitrogen is 120 mm and the partial pressure of oxygen is 80 mm. Okay. According to Henry's law, which gas will dissolve more? Nitrogen will dissolve more, because the partial pressure of nitrogen is more. More the partial pressure, more will be the solubility. Partial pressure of oxygen is only 80. Okay. So, compared to nitrogen, less amount of oxygen will dissolve. Okay. So, this is how we explain Henry's law. Now, this is just a explanation of solubility. Okay. But now, so we'll okay, I will drop that portion now. I will drop this portion. Now, supposing now mathematical expression. Mathematical expression for Henry's law. Okay, this is the statement of the Henry's law. Now, the mathematical expression of the Henry's law. Okay, now we consider now let's make some assumptions. Okay, assumptions are, let A and B be two gases, right? Present over liquid. Okay, present over a liquid. Okay, and let, supposing PA be the partial pressure of A and PB be the partial pressure of B. Now, let XA be the mole fraction of A and XB be the mole fraction of B. Okay, so we can say XA, okay, mole fraction of A and B in the solution, mind you this. Okay, mole fraction of A and B in solution. Okay, so PA and PB, it is the pressure of A and the pressure of B, or partial pressure of A and partial pressure of B on this gaseous portion of the system. Okay, on this over the liquid surface of the liquid. Okay, now once this A and B has dissolved in the liquid, okay, now how much has dissolved, how much of A and how much of B has dissolved, now that is represented by XA and XB. So what are XA and XB? XA is the mole fraction of A in the solution and XB is the mole fraction of B in the solution. Okay, okay, so you should keep this in mind, that this represents the gaseous portion and this represents the liquid portion, the solution part. Okay, so therefore XA is the solubility of A in liquid. Okay, so in this particular Henry's law, the solubility, because solubility again, I told you in the last lecture that solubility is to find out how much of the solute or how much of the gas has dissolved in the liquid. Okay, so that solubility is expressed. I told you there are many ways of expressing solubility. One way of expressing solubility is the mole fraction. Okay, so in the Henry's law, mole fraction is used to express solubility of the gas in the liquid. Okay, so now so we'll continue here. Okay, from there we'll continue here. All right, so now according to Henry's law, this is continued here. Okay, Henry's law, PA is proportional to XA. Okay, now here you might be confused because the statement of the Henry's law is the solubility is proportional to the partial pressure. Okay, the solubility, because solubility is represented by mole fraction. Solubility is represented by mole fraction, and the partial pressure is represented as partial pressure only. Okay, so solubility of A is directly proportional to the partial pressure of A. Okay, all right, but the mathematical but it is the same thing whether you write XA is proportional to PA or PA is proportional to XA. It is the same thing. Okay, because saying X proportional to Y is the same as saying Y proportional to X. Okay, so therefore in the mathematical expression for Henry's law, it is normally written like this. That is PA is proportional to XA. So when PA is proportional to XA, whenever there is expression of proportionality, we have to create a constant. So PA is equal to K into XA. Okay, what is K? Where K is a constant. Okay, now whenever there is solubility, whenever there is a proportionality sign, if you want to simplify it, then we create a constant K, so that PA is equal to K into XA. Okay, and we can solve what is K. How do you solve? So PA is proportional to XA, and in order to simplify the proportionality sign, we write PA is equal to K into XA, where K is a constant. Okay, now in the Henry's law, this constant K is represented by KH into XA, where KH is the Henry's law constant. Okay, so this is the mathematical expression of Henry's law for the gas A. That is, for the gas A, partial pressure of A is equal to KH into mole fraction of A, or the mole fraction of A represents the solubility of A. Okay, now in the same way, similarly you can write down PB will be equal to the mole fraction of Henry's law constant into mole fraction of B. Okay, so for each of the gas A and gas B, you have got a Henry's law expression. Okay, so again briefly I will repeat this. So according to Henry's law, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. Okay, so which means PA is proportional to XA. And to solve for, to simplify this proportionality constant, we write PA is equal to a constant into XA. Okay. Now this constant K is written as KH in the case of this Henry's law. So PA is equal to KH into XA. Okay. This KH represents the Henry's law constant. Okay. So this is the Henry's law constant KH. Okay, and it is significant. Okay. So Okay, so the mathematical form of Henry's law can be, Henry's law is P is equal to KH into X, and KH is known as the Henry's law constant. Okay, KH is known as the Henry's law constant, and X is the mole fraction of gas in liquid, and P is the partial pressure of gas. Okay, all right. Now, what is the unit of KH? Now, unit of KH, whenever you want to find the unit in a particular unit of a quantity or unit of a variable in a particular expression of, then you can deduce it from the expression itself. Okay, so you can see the unit of X, the mole fraction, the unit is, it is unitless. Unitless because it is mole fraction is number of mole divided by number of moles, so it is unitless. But P has a unit. Okay, we have it may be bar, it may be Pascal, it may be millimeter of mercury or centimeter of mercury. Okay, so therefore unit of KH is same as the unit of P. So therefore unit of KH is same as P. Same as P. That is, so those will be bar, Pascal, etc. Okay. Now what is the significance of KH? All right. So you can see from here, okay, we read like this: PH is equal to H into X, or you can see that X and KH has inverse relation, isn't it? X and KH has inverse relation. That is, more the value of KH, less will be X. Okay, so therefore, more KH, less X, or less solubility. Okay, so more KH, less X or less solubility. Okay, so now we will take you to we will just take the help of this chart to apply this particular principle to find out which gas is most soluble and which gas is least soluble. Okay, so from the chart we will just see the chart first. Okay, just see the chart. Okay, so this is a chart showing many gases. Okay, hydrogen, nitrogen, oxygen, carbon monoxide, carbon dioxide, and methane, and against each gas the value of KH is written. Okay, so all the KH, all the values, they are expressed in pascals. Okay, Pascal, K stands for Pascal. Okay, so the first one is hydrogen, 7.12 into 10 to the power of 9 Pascal. The second one is nitrogen, 8.68 into 10 to the power of 9 Pascal. Similarly, we have got many other gases including carbon monoxide, carbon dioxide, and methane. Okay, so now which gas is most soluble in water? Okay, so you can see higher the KH value, less is the solubility. Okay, so the highest value of KH is that of nitrogen. Highest value of KH is that of nitrogen, which is 8.68 into 10 to the power of 9 Pascal. Okay, that means nitrogen is the least soluble out of all these 5 gases, right? And you can also see that the least value of KH, will mean that the gas is most soluble in water. Okay, so the least value of KH is that of carbon dioxide. Okay, it is 0.167 into 10 to the power of 9 Pascal. Okay, so therefore carbon dioxide is the most soluble out of all this. Okay, and all of you know all of you know that we have all day-to-day experience or common experience also that carbon dioxide is more soluble than all these gases. Okay, because that is the reason why carbon dioxide is also present in aerated waters. Okay, so that's how you apply the concept of KH or the significance of KH on the value of solubility of a gas in a liquid. Okay, so now we'll come back to the main topic. Now next what we'll do now is we'll take up one problem on Henry's law, okay, and then that will be the end of Henry's law. Okay, this was the slide that I gave you in the first lecture actually. Okay, but out of this slide we could attempt only 3 problems. First only. Okay. So there are many other problems which you can attempt, because we have studied about molarity, etc. We have studied about the other forms of concentrations in the second lecture, so you can attempt these other questions also. Today we will just do question number 11, which is a question based on the Henry's law. Okay, so question number 11: methyl bromide is a gas used as a soil fumigating agent. If its solubility in water at 25 degrees centigrade is 0.026 m, small m, molal, and the partial pressure is 125 millimeter of mercury, calculate the Henry's law constant in atmospheric units. Okay, atmospheric units. Okay, so again I am repeating the question, and then we will take up this example. We will take up this problem in the green board. Okay, so again I am repeating the question. Methyl bromide is used as a soil fumigating agent. Okay, methyl bromide is a chemical and it is used as a soil fumigating agent. Its solubility in water is at 25 degrees centigrade is 0.026 molal, and the partial pressure is 125 mm of mercury. Calculate the Henry's law constant in atmospheric units. Okay, so let's come to the green board and then solve this problem. Okay, so the expression that we use is the Henry's law expression, P is equal to KH into X. This is the expression that we'll be using, and the question is now the question is to find KH, but X is not given. X is not given. X is the mole fraction, but the solubility is expressed in another unit, which is molal, M-O-L-A-L, molal unit. Okay, so what we'll do now is convert this solubility in molal strength to mole fraction. Okay, so 0.026 m means 0.026 mole of methyl bromide is present in 1000 grams water. Okay, 1000 grams of water. Okay, so therefore now 1000 grams of water means 1000 divided by 18 is equal to 55.5 moles of water. Okay, so now once you know this, what will be the value of X? Mole fraction of methyl bromide is how much? It is the number of moles of methyl bromide, which is 0.026 divided by the total number of moles. Okay, so this is 0.026 plus 55.5. Okay, so let's solve this particular mathematical sum. To be 0.00046. This is the mole fraction of methyl bromide in the in that solution. Okay, methyl bromide in the solution. Now the next is the P, what is the value of P? The value of P is 123 millimeter of mercury. Okay, 123 millimeter of mercury. Okay. Now, the question asks, the question tells us to find the answer in atmospheric units. Now, in atmospheric units, now 1 atmosphere is equal to 760 millimeter of mercury. Okay, so therefore, if you want to convert millimeter of mercury to atmosphere, you divide by 760. So it will be 123 divided by 760. 123 divided by 760. So let's solve this also. So this will be equal to 0.1618 atmospheres. Okay. So once we have got the mole fraction and we have got the partial pressure, then we can easily find the value of KH. How? Okay, you just let's come to this. Come to the solution part. So therefore, P is equal to, so here again, okay, this. So P is equal to KH into X, and KH is equal to P upon X. Now, what is the value of P? The value of P is 0.1618 divided by, and the value of X is 0.00046. Okay, and the answer is naturally in atmosphere because P is in atmosphere. Okay, so let's solve this. So you are getting 3.51 into 10 to the power of 2 atmospheres. Okay, so this is the answer that you are getting, 3.51 into 10 to the power of 2 atmospheres. And this is the answer that you will find in the back of the your book also. Okay, numerical also. Okay, so this is how you problems on Henry's law. Okay, so once you know the partial pressure and once you know the mole fraction, then you can find KH. Or if you know KH and if you know the pressure, then you can also find out how much of gas has dissolved in the liquid. Okay, so we will. This is the last topic that I will take up in today's lecture. This. Again, the solubility of a gas in liquid. Okay, what are the we are just studying about what are the different factors that on which the solubility of a gas depends. Okay, so the next and the last factor most probably is the dependence on temperature. Okay, so see, whenever a gas is dissolved, okay, in gas A and gas B, okay, or simply one gas, no problem. Okay, so whenever gas is dissolved in a liquid, all right, how much of the gas has dissolved depends upon temperature of the liquid also. Why? Because when the temperature is high, okay, it causes the gas particles to escape from the liquid. That means what? The more the temperature, the less will be the solubility of a gas in a liquid. Okay, more temperature, less solubility. Less temperature, more solubility. Okay, so there is a direct you can say dependence of solubility and temperature. That is, solubility we can say of a gas decreases with the increase in temperature. Increase in temperature of the liquid. Okay, and so you can apply this particular phenomena to say the life in underwater creatures. Okay, so when the temperature is high, Supposing in a lake or in a river, when the temperature is high, what does it mean? That means the aquatic life, aquatic creatures will have less amount of oxygen to breathe. Okay, all right. More the temperature, the more the temperature of the river, the less will be the amount of oxygen that is dissolved in the river. Okay, so therefore, high temperature in the rivers or lakes or seas, it is not conducive to the creatures living in the living under water. Okay, so that is simply how solubility depends upon temperature. Okay, now we have a chart. Okay, we have a chart which we will discuss just to show how solubility of a gas depends upon temperature. The solubility of different gases in water at different temperatures, okay. So now this only solubility is written here, okay. So the this amount is actually grams per 100 grams of water. Yeah, the amount of gas, so it means 0.15 here means 0.15 grams of acetylene in 100 grams of water. Okay, this means 0.117 grams of acetylene in 100 grams of water, and so on. Okay, so you can see that this is at a temperature of 283 K. The next one is a temperature of 293 K. Okay, so in temperature is increasing. Temperature is increasing. So you can see as the temperature increases, the solubility of acetylene, what is happening? It is decreasing. Okay, it was highest. The solubility was highest when the temperature was 283, but the solubility is the least. Okay, 0.094 grams per 100 grams. The solubility is the least when the temperature becomes 303 Kelvin. Okay, similarly, any other gas, supposing let's take example of oxygen gas. 283 Kelvin, it is 0.0053 grams. But at a higher temperature, 303 K, it becomes 0.0036 grams. Okay, so you can see how the temperature is affecting solubility. Okay, so this is all that we will do today. Okay, so we have studied today about most important about the Henry's law, which is a quantitative description of how solubility depends upon the pressure of a gas. Okay, you have studied about Henry's law, mathematical expression. Okay, the meaning of the significance of KH or the Henry's law constant, and also how to solve problems on the Henry's law mathematical equation. Okay, and we have also studied just now the dependence of solubility on temperature. Okay, so that's all for today. Okay, see you again in the next class. Okay.